Hello and welcome to my presentation on gated recurrent units or GRUs. So to understand GRUs, you need to understand LSTMs, which are long short-term memory networks, and to understand LSTMs, you need to understand recurrent neural networks, RNNs. So GRUs were introduced in 2014 as a simpler and faster alternative to LSTMs, and they've become one of the most popular RNN architectures for sequence and time series prediction. So we'll start with RNNs. Traditional RNNs suffer from short-term memory. They can't reliably remember information from earlier in a sequence, so they fail in tasks that require context, like autocomplete or predicting the next word in a sentence. In a sentence like, JJ plays basketball every day, it shouldn't be hard to guess that his favorite hobby is blank. The model should connect the word basketball with the word sports. For example, if we want to predict the word sports in this context. But an RNN forgets that keyword before it reaches the prediction point. So, for example, let's say it remembers just the previous two words. It'll just remember the word hobby is before it gets to predict the next word here. So how do we solve this problem? This problem is also known as the vanishing gradient problem. And this is solved by introducing LSTMs. So say the word is sports that we need to predict. So LSTMs remember certain keywords in a sequence. So we do not remember the word JJ, we do not remember the word plays, but once the word basketball hits the unit, it's going to remember it. So it's going to carry the word basketball over and over and over up until the point where it is required to predict. So it can keep the word basketball and it can directly connect the word basketball to sports. So a GRU is basically a evolution of LSTM. So LSTMs have three gates: the input gate, the output gate, and the forget gate. GRUs only have two gates: the update gate and the reset gate. So how do these work? This is a GRU box, a simplified version. So what the update gate does is it controls how much past information to keep. The reset gate controls how much to forget. So this lets the network carry information forward when it matters and discards it when the context changes. So what we have here, HT-1, that's the previous hidden state. And this is the current input state. So what is a hidden state, you may ask? Okay, simply put, it's the model's memory at a given moment. So it is the compressed summary of everything that the model thinks is important so far. So for example, you read in the sentence, JJ plays basketball. So it remembers the word. Let's say JJ plays. It'll store that context, JJ plays. After reading the word basketball, it's going to update the context. So this evolved understanding of what the context is known as the hidden state. So the hidden state carries information from the past. The hidden state gets updated at every time step, and the hidden state is passed forward to help make future predictions. So let's say we have a longer statement here. JJ plays basketball every day. Shouldn't be hard to guess that his favorite hobby is sports. That's grand. However, his friend Finn likes painting. Now we have a new keyword, painting, and drawing. So how will a GRU handle this new context, you may ask? So let's say we want to predict the word art, but let's say we don't know the word art. So this is what a GRU will do. At the reset gate, once the word painting is introduced into the sequence, then a sigmoid function is applied to these two words. And the purpose of this sigmoid function is to make the network forget the word basketball. So this is the equation of a reset gate. So your output here is equal to a sigmoid product function of the previous inputs. You can see here WR, UR, meaning reset, reset. The next gate is the update gate. So once the word draw hits the model, then it knows the context. Retain the word painting. And another sigmoid function is applied in this gate. So you can see that some of the letters changed. You have U of Z now, WZ, ZT, as compared to the U of R, W of R, R of T. So you may ask, what is a sigmoid function? It's just a function that turns numbers into values between 0 and 1. So a value of 0 means ignore completely. That's what the reset gate would do. And a value of 1 would be keep everything. So for example, in this case, we probably have a sigmoid function of 1 or of 0.95, something like that. So think of it as a volume knob. 0 is mute and 1 is full volume. Anything in between is just a partial signal. So the update gate uses the sigmoid and answers the question, how much should I remember? So this is the final GRU box. In your update gate, you have your sigmoid functions. And the newest thing here is this, which is a Hadamard product. The Hadamard product is simply a matrix multiplication, an element-wise matrix multiplication, and it helps update the hidden state. So it lets the network keep some information and suppress the rest, element by element. And all this happens when now you can get your output and you can get your next hidden state. Thank you for listening to this presentation on GRUs, and I appreciate your time.